morning, gotta be fresh, gotta go downstairs, gotta have my bowl, gotta have cereal, seeing everything, the time is going, ticking on and on, everybody's rushing, gotta get down to the bus stop,
I can't
gotta
put up
catch
with
my
you
bus,
anymore.
I see my
John, stop it please right now. Okay, today's lesson it's about intra and intermolecular forces. Let me to start with intramolecular forces. We have two types of intramolecular forces. Anionic bonding and covalent bonding. Anionic bonding is formed by the attraction of positive ions to negative ions. In general, an ionic bond is formed when an electron from one atom is transferred to another atom, so as to create one positive ion and one negative ion. Okay, the next part is about covalent bonding. The covalent bond is formed when two atoms having less than full shells of electrons are able to share one or more of their electrons with each other to attain full electron shells. We use Lewis structure to show how the valence electrons are distributed in an atom, ion or molecule. I will give you one example of the Lewis structure after watching this video clip.
Sodium and chlorine are examples of atoms that combine ionically. Sodium is a reactive, soft, silvery metal of low density. Its atoms have one valence electron. Chlorine is a corrosive, yellowish-green gas. Its atoms have 7 valence electrons. When mixed, the two atoms combine explosively as an electron moves from each sodium to each chlorine atom. A closer look at the resulting product reveals the formation of small white sodium chloride particles, also known as table salt. Water is an example of a compound containing two oxygen-hydrogen covalent bonds. Hydrogen is a colorless, explosively reactive gas. Its atoms have one valence electron. Oxygen is a colorless, reactive gas. Its atoms have 6 valence electrons. When the two gases are mixed, a spark will cause them to react. The atoms explosively combine as a pair of electrons become shared between each oxygen and 2 hydrogen atoms. A closer inspection of the inside of the container shows water vapor condensed on the cool container walls. Here is the same reaction in a different setting.
Bravo! Bravo! Encore!
John, please come down. Now let me to talk about the electronegativity, which is the tendency of the atom to attract electrons from a neighboring atom. In general, when going from left to right across the periodic table, the electronegativity of the atoms will increase, and when going down a family of the periodic table, the electronegativity of the atoms will increase as well. From the electronegativity we can understand if an atom has a high electronegativity. It strongly attracts electrons from a neighboring atom and may completely remove an electron from the neighboring atom. As a result, these valence electrons are difficult to remove and the atoms has a high ionization energy. Okay, John, can you please explain how to predict when an ionic bond will form? Ionic bonds are formed when elements from opposite sides of the periodic table are combined. That is, when a metal and a non-metal are combined. Good job, John. It's good to know that there are two classes of covalent molecules, truly covalent molecule and polar covalent molecule. These two classifications of covalent molecule are very related to the electronegativity. If the difference in electronegativity becomes 0.2 or smaller, it's a truly covalent molecule, but if the difference in electronegativity becomes 0.3 to 1.6, it's polar covalent molecule. If the difference of electronegativity exceeds from 1.6, we can say that it is ionic. As I promised, let's see the video clip of Mr. Richardson, which is about how we can apply the Lewis structure to show the distribution of atoms in an atom. Before we start the video clip, I want to talk about the octet rule that states atoms in columns 14 to 17 of the periodic table tend to form covalent bonds so as to have 8 electrons in their valence shells. To draw the Lewis structure first, we must decide on the skeletal structure, which is always the least electronegative atom is usually in the center. The second step is to count all the valence electrons and place electron pair in each bond and complete the octet of atoms other than the central atom. Any leftover electrons go on the central atom in pairs. In the other hand, if the central atom still has less than an octet, move electrons pairs to make double or triple bonds. Let's watch the video.
And the last example in your handout, sulfur dioxide, SO2. So following the same steps, sulfur is the least electronegative. It's also the element written first, so that's your clue. It will go in the center, and we'll put the oxygens symmetrically on either side. Let's count up the valence electrons. Sulfur is 6, and oxygen is also 6, and you've got 2 of them, so that makes 12. A total of 18 valence electrons. Let's put in the 2, at least 2, that are going to bind the sulfur to the oxygen. And the next step would be to complete the octets for the atoms on the outside. Would be our oxygens. So right now we have 2, 4, 6, 8, 10, 12, 14, 16 electrons. We have 2 more electrons to draw in, and the next step indicates we would put those on the center atom, the sulfur. Now we have a problem. The oxygen octets are completed, but the sulfur is not. It only has 6 electrons. It needs 2 more. Where are they going to come from? They're going to come from one of the oxygens. So these electrons here, it doesn't matter which oxygen we choose. Let's just take these ones. These 2 are going to be shared, and I will erase those 2 there. Now the sulfur has 8, oxygens have 8, and we've drawn 18 electrons. Let's clean this up. Sulfur, a double bond on this side to the oxygen, and a single bond on this side to this oxygen. Okay, and we're finished for now. It actually wouldn't matter which oxygen you made the double bond to. The next topic we're going to look at is resonance structures, but we'll save that for the next video. And the last example in your handout, sulfur dioxide, SO2. So following the same steps,
I actually talked about the resonance last year. Anyway, John, can you please give me the explanation of the resonance? I have no idea, Mrs. Langdon. It's okay. Resonance applies when Lewis structures do not agree with lab measurements of bond length and bond strength. John, did you get it? Can I move on? Yes, I got it. Bravo. Now I want to talk about the valence shell electron pair repulsion theory. Is a model in chemistry used to predict the shape of individual molecules based upon the extent of electron pair electrostatic repulsion. It is also named the Lesby-Nyholm theory after its 2 main developers. When we want to draw the valence shell electron pair repulsion theory, it is good to know that the number of electron pairs surrounding an atom, both bonding and non-bonding, is called its steric number. Now let's watch the video clip to understand this important theory in chemistry.
Section A, the VSEPR theory.
Scientists have developed a number of theories about how atoms arrange themselves in a molecule. The shape the atoms form in a molecule is called molecular geometry. A common model used to predict molecular geometry is the valence shell electron pair repulsion model, known as the VSEPR model. The VSEPR model predicts molecular geometry by describing how electron pairs bond and theorizing how electron pairs and bonds will affect the shape of the molecule. According to the VSEPR model, the electron pairs in a molecule's valence shell are arranged so that they're as far away from each other as possible. In other words, the electrons act like they repel each other.
Whenever you're trying to predict molecular geometry, be sure to VESPER.
The VSEPR model says that a molecule with two pairs of shared electrons has a linear shape. Using the VSEPR theory, if you know that a molecule has two pairs of shared electrons, you can predict that the molecule will have a linear shape. This linear-shaped molecule is represented by the notation AX sub 2. The sub 2 tells you that there are two pairs of shared electrons.
AX sub 2. Linear!
A molecule with three pairs of shared electrons is called trigonal. And here's a picture of what the VSEPR theory says it looks like. Trigonal molecules, those that have three pairs of shared electrons, are represented by the notation AX sub 3. The sub 3 tells you that the molecule has three pairs of shared electrons.
Molecules can also have non-bonding electron pairs. The non-bonding electron pair takes the place that a regular bond would occupy. We will use water again as an example, but know that this example shows you only one of the many possible arrangements of bonds and atoms. Be sure to check out the others in your textbook.
I'm checking out the other arrangements in my textbook.
Water has two bonds between hydrogen and oxygen, but oxygen also has two non-bonding electron pairs. This gives water a tetrahedral arrangement of electron pairs and bonds. Since diagrams don't usually show the non-bonding electrons of oxygen, we usually just say that the water molecule is bent, rather than referring to it as tetrahedral.
That's bent, bent, bent.
Bravo! Bravo! Encore!
Okay, I hope you get the concept of intramolecular forces by watching this video clip. We finished the intramolecular forces. Now we are ready to move on. Now we will start the next unit, which is intermolecular forces. The physical properties of melting point, boiling point, vapor pressure, evaporation, viscosity, surface tension, and solubility are related to the strength of attractive forces between molecules. These attractive forces are called intermolecular forces. The amount of stick-togetherness is important in the interpretation of the various properties. There are three types of intermolecular forces: 1 van der Waals forces, dipole-dipole forces, and hydrogen bonding. What is van der Waals forces? Van der Waals forces include attractions between atoms, molecules, and surfaces. They differ from covalent and ionic bonding in that they are caused by correlations in the fluctuating polarizations of nearby particles. Intermolecular forces have four major contributions: act on all atoms and all molecules, whether polar or non-polar, are responsible for the condensation, at very low temperature, are the result of momentary shifts in the symmetry of the electron code of a molecule. Section 2. What is dipole-dipole interaction? Dipole-dipole forces are bonding forces which exist as a result of an electrostatic attraction between molecules having permanent dipoles. By the way, the dipole is a partial separation of charge which exists when one end of a molecule or bond has a slight excess of positive charge and the other end of the molecule or bond has a slight excess of negative charge. In addition, if a permanent dipole is absent, then only London forces are present. What is the hydrogen bonding? A hydrogen bond is the attractive interaction of a hydrogen atom with an electronegative atom, such as nitrogen, oxygen or fluorine, that comes from another molecule or chemical group. The hydrogen must be covalently bonded to another electronegative atom to create the bond. These bonds can occur between molecules intermolecularly or within different parts of a single molecule.